Welcome to the General Chemistry 2 class. This section is on physical properties of solutions. This lesson is about solution stoichiometry. Let's begin. In this lesson, we will perform stoichiometry calculations for reactions in solution. Dilution is a process of preparing a solution of lower concentration from a solution of higher concentration, which is called a stock solution. Addition of solvent in a solution affects the concentration of the solute but not its amount. Thus, most solute before dilution is equals to most solute after dilution. From the definition of molarity, the amount of moles can be determined using the equation amount of solute in moles equals molarity times volume of solution. With this, the first equation is transformed into M1V1 equals M2V2. The subscript 1 denotes the solution before dilution, while the subscript 2 denotes the resulting solution after dilution. Example 1. What volume of 0.500 molar sodium hydroxide is needed to make 100 milliliters of 0.125 molar sodium hydroxide? The volume of the original or stock solution is missing in the problem. To solve for this volume, we will use the equation M1V1 equals M2V2. Solving for V1, we have V1 is equals to M2V2 divided by M1. Substituting the given values, we get V1 is equals to 25 milliliters. Example 2. What is the final concentration of potassium permanganate in a solution if 24.70 milliliters of 0.9847 molar stock solution is brought to a final volume of 100 milliliters? Solution. Final concentration is missing in the problem. M1V1 is equals to M2V2. Solving for M2, we have M2 is equals to M1V1 divided by V2. Substituting the given values, we get M2 is equals to 0.2432 molar. Now, let us proceed to reactions occurring in solutions. These reactions include neutralization and precipitation. Neutralization is the reaction of an acid and a base. Precipitation is the reaction that involves production of a water-insoluble product from water-soluble reactants. The equation for a reaction occurring in reactions can be written in the form of a formula equation, complete ionic equation, and net ionic equation. The formula equation shows the compounds used as reactants and the compounds formed in the reaction. In a complete ionic equation, all the ionic compounds that are dissolved in water are dissociated into ions, while the precipitate is not taken as a dissociated compound. The net ionic equation considers only the ions directly involved in the reaction. The ions not directly participating in the reaction, called separator ions, are no longer included. Consider the precipitation of barium sulfate from sodium sulfate and barium chloride. The formula equation shows the formula of sodium sulfate and barium chloride, both in the aqueous phase, as well as the formula of the product, solid barium sulfate and sodium chloride in the aqueous state. The complete ionic equation shows that sodium sulfate, barium chloride, and sodium chloride are dissociated into ions, leaving barium sulfate undissociated. In the net ionic equation, barium and sulfate ions are left as reactants, since they are the ions involved in the formation of barium sulfate precipitate. Consider the neutralization of a hydrochloric acid solution by a sodium hydroxide solution. The formula equation shows the reaction of aqueous hydrochloric acid and sodium hydroxide solutions to form water and aqueous sodium chloride. For the complete ionic equation, hydrochloric acid, sodium hydroxide, and sodium chloride are dissociated into ions. For the net ionic equation, only hydrogen and hydroxide ions are left as the reactants and water as their product. This equation is same for any neutralization reaction in aqueous solution. Here are the general steps in solving problems on solution stoichiometry. Number 1. You must note the reactants present and the products formed in the reaction. Number 2. You must be able to come up with a balanced equation for the reaction. Number 3. Dealing with stoichiometry of solutions is similar to solving a typical stoichiometry problem. The only difference is that the quantity of a reactant or product is expressed in terms of concentration and volume. It is also important to consider the balanced chemical equation in solving the problem, since mole ratio is involved in the calculation. Number 4. Determine the limiting reactant by calculating the amount or mass of product, if applicable. Number 5. Express the answer in terms of the desired quantity. Example number 3. Consider the precipitation of barium sulfate from sodium sulfate and barium chloride. What is the maximum mass of barium sulfate that can be formed by mixing 40 milliliters of 0.050 molar barium chloride and 25 milliliters of 0.1 molar sodium sulfate? The foremost step in solving the problem is writing the balanced chemical equation. For this problem, the net ionic equation suffices since only barium and sulfate ions are involved in the reaction. The equation is given by 1 mole aqueous barium ion plus 1 mole aqueous sulfate ion producing 1 mole barium sulfate precipitate. Calculate the maximum mass of precipitate that can be formed from each reactant. For barium chloride, 1 mole of the compound produces 1 mole of barium ions. Thus, the number of moles of barium ion equals the molarity times the volume of the barium chloride solution, which is equals to 0.003 moles. We need to convert moles of barium ion to mass of barium sulfate precipitate by multiplying moles barium ion times the mole ratio 1 mole barium sulfate per mole barium ion times the molar mass of barium sulfate. Use your periodic table to calculate the molar mass. The mass of barium sulfate is 0.7 grams. Consider sodium sulfate, in which 1 mole of it produces 1 mole sulfate ion in the solution. The amount in moles of sulfate equals the molarity times the volume of sodium sulfate solution. From our calculation, we get 0.0025 moles barium ion. To convert moles barium ion to mass of barium sulfate, multiply the number of moles barium ion by the mole ratio. 1 mole barium sulfate per 1 mole barium ion, then by the molar mass of barium sulfate. The answer is 0.584 grams barium sulfate. The limiting reactant or reactant that gives lower amount of product dictates the maximum amount of product that can be produced. Sodium sulfate gives lower amount of barium sulfate with a value of 0.584 grams. Thus, mixing the two given solutions can produce up to 0.584 grams of barium sulfate. Example 4. Lead 2 iodide is precipitated upon mixing solutions of lead 2 nitrate and potassium iodide. Calculate the minimum volume of 0.4475 molar lead 2 nitrate that must be mixed with 12.35 milliliters of 0.8491 molar potassium iodide to allow complete precipitation of lead 2 iodide. Solution. Write the balanced net ionic equation for the reaction. The equation is given by 1 mole aqueous lead 2 plus ion plus 2 moles aqueous iodide ion producing 1 mole lead 2 iodide precipitate. Calculate the amount in mole of iodide. From potassium iodide, in which 1 mole of the compound produces 1 mole iodide ion, moles iodide ion equals the molarity times volume of potassium iodide solution. The answer is 0.010486 moles iodide ion. Convert this value to moles lead 2 plus ion. Multiply moles iodide by the mole ratio. 1 mole lead 2 plus ion per 2 moles iodide ion. The answer obtained is 0.005243 moles lead 2 plus ion. Calculate the volume of the lead 2 nitrate solution from the calculated amount and the given molarity. The volume of solution equals moles lead 2 nitrate divided by molarity. The answer equals 0.00172 liters or 11.72 milliliters. This means at least 11.72 milliliters of the lead 2 nitrate solution is needed for the complete precipitation of lead 2 iodide. As mentioned earlier, neutralization is the reaction between an acid and a base. There are various ways of defining acids and bases. For instance, Arrhenius defines an acid as the substance that releases proton in water, while a base releases hydroxide ion in water. In a more generalized perspective, Bronsted and Lowry define an acid as a proton donor while a base is a proton acceptor. Details on acids and bases will be discussed in another lesson. Example 5. What is the concentration of a hydrochloric acid solution if 50 milliliters of this solution requires 15.50 milliliters of 0.08975 molar sodium hydroxide to be neutralized? Solution. Write the balance formula equation for the reaction. For neutralization reaction, this type of equation is more conventional to clearly see the mole ratios of the acid and base that are reacting with each other. Calculate the amount of sodium hydroxide using the molarity and volume of the sodium hydroxide solution. The answer is 0.0013911 moles sodium hydroxide. From the balance equation, the mole ratio is 1 mole hydrochloric acid per 1 mole sodium hydroxide. Thus, the number of moles of hydrochloric acid is also 0.0013911 moles. Dividing the number of moles of hydrochloric acid by the volume of the solution gives its molarity. The molarity is 0.02782 moles per liter or 0.02782 molar. Example 6. What volume of 0.6497 molar potassium hydroxide solution is needed to completely neutralize 25 milliliters of 0.2419 molar sulfuric acid solution? Solution. Write the balance formula equation for the reaction. 1 mole aqueous sulfuric acid reacts with 2 moles aqueous potassium hydroxide to produce 2 moles water and 1 mole aqueous potassium sulfate. Calculate the amount of sulfuric acid by multiplying the molarity and volume of sulfuric acid solution. The answer is 0.0060475 moles sulfuric acid. Next, convert moles sulfuric acid to moles potassium hydroxide using the mole ratio. Based on the balanced chemical equation, 2 moles of potassium hydroxide reacts for every 1 mole sulfuric acid. Thus, the moles potassium hydroxide equals 0.01207. Thus, the moles potassium hydroxide equals 0.01295 moles. Calculate the volume of potassium hydroxide solution from the calculated amount in moles and the given molarity of potassium hydroxide. The volume of solution equals moles potassium hydroxide divided by its molarity. The answer is 0.01862 liters or 18.62 milliliters. Practice 1. Calculate the mass in grams of iron 2 sulfide that can be generated by mixing 15 milliliters of 0.1493 molar iron sulfate and 17.50 milliliters of 0.1097 molar sodium sulfide. 2. A 25 milliliter acetic acid solution requires 15.47 milliliters of 0.6574 molar sodium hydroxide for neutralization. What is the molarity of the acetic acid solution? Provide a solution for each problem to arrive at the given answer. To summarize, in a solution, dilution of a solute lowers its concentration, not its amount. Equations for reactions occurring in solutions can be written in the form of a formula equation, complete ionic equation, or net ionic equation. Some reactions in solutions include precipitation and neutralization. Stoichiometric calculations involving solutions take into account the solution concentration and volume of the solution to determine the amount of solute. To learn more about this lesson, kindly visit these references. That's all for this lesson. Thank you.